I want to thank IFMA Boston for inviting us to join this Tech Talk panel. Definitely cannot promise any subject matter expertise, but Erik and I are really glad to share our experiences with all of you. I'm Kate Loosian. I'm the Director of Facilities Management at the Harvard Radcliffe Institute.
Our presentation today will focus on the geothermal wells that we utilize on our campus. So let's begin by giving you a little history.
In 2003, a decision was made to install 2 geothermal wells as part of a renovation of the historic Radcliffe Gym, which you'll also hear referred to in this presentation as the Knaufel Center. It was renamed about 10 years ago. The project was looking to integrate sustainable technologies, and due to the 4-sided visibility of the building, it was really difficult to find a good location for cooling towers and condensing units, so that led us toward geothermal. This was about 20 years ago, and this was a sustainability initiative somewhat ahead of its time. And initially, it was successful. The building was able to take advantage of open-loop geothermal well technology. Over the past few decades, open loops have been replaced in many cases with closed-loop systems. However, a key advantage to an open-loop system is capacity. With an open-loop system, there's a fairly constant renewal of stable temperature water available, making capacity a key factor, especially when looking at larger commercial buildings. As many of you may know, when utilizing geothermal wells in the northeastern section of the United States, we are not utilizing the well system just to only heat our buildings.
You know, many people think, when they think about geothermal wells, of harnessing very hot water, right? And of course, in some parts of the country, geothermal heat is a gift. Free heat and as much of it as you need. However, in New England, we utilize the wells not only to heat our buildings, but also to cool our buildings. We can reject the heat from our buildings back to the earth, and the wells serve as the water for our water-cooled heat pump units. The wells are used much more like a battery bank, right? We can put heat energy from our buildings in the summer and put it into the earth. We can take it from the buildings and put it in the earth in the summer. And in the winter, we can pull the heat from the earth and put it into our buildings. Now, the success of the well system is the fact that the underground aquifers provide a year-round supply of approximately 55-degree water. Now, couple this with the second law of thermodynamics, and in simple terms, it states that heat will always want to travel to the cold side of things, to balance it out. And we have a wonderfully sustainable thermal energy system in our wells. Now, in 2004, the creation of 2 wells was completed. And that served our conference building, the Radcliffe Gym, or Knaufel Center, now renamed the Knaufel Center. And on the heels of this success, in 2007, 5 more wells were installed to serve our office building, Byerly Hall. Now, let's talk quickly about the installation of the wells. For this instance, I want to look closer at the Byerly Hall wells.
So the wells start at the surface of the earth. A 6-inch hole is drilled down 1,500 feet. This is approximately the depth of 2 John Hancock buildings stacked on top of each other. The holes penetrate the ground layers all the way to bedrock. It's the bedrock where fissures in the rock provide access to underground water. I'm going to pause here and I'm going to debunk this slide because it looks really nice, but it's not really nice. So we'll start by, I'm going to ask you to consider how small the 6-inch diameter hole is. That's not a big hole, right? If you're like me, when we installed these wells in 2003, you're picturing a really nice plumb column with straight, even sides that goes straight down into the plane. And I'm telling you right now, you have to erase that image. Not like that. Over a length of 1,500 feet, that narrow 6-inch diameter hole can migrate as much as 10 feet horizontally, so it's not straight and plumb. And if you stop and think about water fissures in bedrock, you think about the fact that it's actually really down there in an ever-changing environment. Those cracks are evolving all the time, and the water is continuing that evolution. So there's debris, and the wells shift, the rock shifts. It's an ever-changing environment. So now that you think of that well as a fairly unscientific and messy installation, we'll go back to the description of the system. After you've drilled that hole down 1,500 feet, you extend a 4-inch pipe all the way to the bottom of the well, with a pump about 150 feet down. The pump pulls through the pipe up from the bottom of the well. The water passes then into the building through heat pumps, where thermal energy is either extracted or rejected from the water, depending on whether we're trying to cool or heat the building. The water is then pumped back from the building into the well, using the remaining 2-inch area outside the pickup pipe to return to the earth. I'm going to stop, and I'm going to ask you to remember this point. In its original installation, the well water was returned to the top of the well and fell back into the well in that small area between the wall and the pickup pipe. We'll have a sketch of that later, so just please keep it in mind.
Now, these wells were successful in their early years of service, but trouble was brewing underground. As slowly, the efficiency dropped, and the wells became inefficient over time, to the point in about 2012 when they became unusable. So, this leads us to the crux of our presentation. What went wrong? What happened to the functioning well system? When dealing with underground systems, there is a difficulty in fully understanding the issues that plague the wells. The issues could lie hundreds of feet below the surface. And you really need to drill down to the root of the problem. That was an intended pun. What we noticed are the following issues. Low water flow, which can translate into an incorrect energy exchange, or in other terms, a lack of delta T, or change in water temperatures across the heat pump heat exchangers. What is causing the low water flow? Is the well collapsing? Are the pickups clogged? Is there something we are missing that may be a simple fix? Or is the issue much larger? Now, many questions needed to be considered. Another issue that was recognized in the early stages of troubleshooting was visible damage to the heat pump's heat exchanging equipment. The heat pumps were becoming increasingly worn. The heat exchanging tubes were slowly being eroded away. Now, this is alarming, as it's not a simple or inexpensive solution to replace the heat exchanging parts of a heat pump. A full heat pump replacement may be needed in many cases. The final part of this challenge relates to what we found while digging deeper and looking into the low water flow issue. An enormous amount of what appeared to be rust. Yes, rust. This rusty material turned out to be iron bacteria. Now, you may initially think this buildup may be caused from accumulated debris circulating from the well itself. But this material is actually organic material, an organic iron bacteria. Now, iron bacteria are small living organisms that occur naturally in soil, shallow groundwater, surface waters, and these bacteria combine iron or manganese and oxygen. Now, I need you to remember the key word oxygen. We'll make note of it in a little bit, to form deposits of rust, bacterial cells, and a slimy material that sticks the bacteria to well pipes, pumps, and plumbing fixtures. Thank you, Wikipedia, for that explanation. There was an enormous amount of this iron bacteria clogging our system, and the wells became unusable. These factors were all part of what our challenge was. So what did we do to fix it? We needed to understand the root of the problem, which for the most part was the iron bacteria. The iron was causing the low water flow, the lack of delta T, and the equipment deterioration. And filtration will only help so much, as the filtration is inside the buildings. There's still another 1,500 feet of plumbing below the ground that is susceptible to iron buildup. And regular maintenance to clean or replace the piping would not be sustainable, and the cost would certainly outweigh the benefits. More needed to be understood. In working with consultants, educated contractors, design professionals, engineers, and even students, a solution was not just one action. There needed to be multiple actions that combined provided the solution. So now let's dive into what actions we took.
The first thing we needed to do was redevelop the wells. With the excessive buildup of iron bacteria, the wells themselves actually needed to be cleaned. And again, I'll remind you of that very small diameter hole. It's less than plumb, 6-inch column. We redeveloped the holes by removing the 4-inch pipe and boring out the entire length of the well holes, basically re-drilling.
We also needed to separate the well water from circulating directly into our heat pumps. Now, this required the addition of a closed-loop heat exchanging system comprised of plate and frame heat exchangers. Here you can see a picture similar to the one we use in our mechanical rooms. And it's a closed-loop heating exchanging system was installed in between the well water and the heat pumps themselves. Now, this allowed a thermal exchange of energy between our heat pumps and the well water without the abrasive well water damaging our equipment. Now, granted, we have introduced another level of heat exchange here, but for our purposes, it worked and created a level of separation we needed to prevent damage. Now, in addition to this, a much more robust filtration regimen was installed. Bag filters, you see to the right of the plate and frame here, were installed to filter the well water as much as possible without creating too much resistance to flow. And these steps really started us on the path to begin revitalizing our water-cooled heat pump system.
So going back to that great obstacle, the iron bacteria, we had really seen how damaging it was and how it seemed not to necessarily stop and go away. So we're going to look at the two things that we asked you to keep in mind during our early part of the presentation. The first that we mentioned a short time ago is that the return water was put in the well, back in the well at the top, and it utilized that space between the pipe and the wall of the well to return back to the water table. The second is that iron bacteria needs oxygen to grow. So the breakthrough in our investigation of our wells is that the return water being deposited at the top of the well, falling through that void around the pickup pipe, was becoming heavily oxygenated. It was bubbling up. It was bubbling its way down, whatever, sound effect. Sorry. So the wells kind of really, we created a perfect breeding ground for continued development of iron bacteria. And with that information, we were able to come up with a solution to this problem. And this was really the primary intervention we took to rehabilitate the system.
Yeah. So you can see this next slide is a good, this is the original slide. You can see that water kind of getting deposited and falling. The change was, now we needed to return that water to the bottom of the well, as Kate mentioned. So reversing the direction of the water flow to drastically reduce oxygenation of return water was paramount. To accomplish this, we replaced the 4-inch pipe with a 2-inch pipe that extended to the bottom of the well, and the return water was now being forced to the bottom of the well, released through perforated piping in the lower 200 feet of piping. This eliminated some static pressure issues for just directly putting it to the bottom through a closed pipe. And this eliminated the water falling through a column of air, right, significantly reducing the oxygenation. The pump was moved from the inside of the pipe to the outside of the pipe and now pulled the well water from the area between the well wall and exterior circumference of the pipe. Now, it's important to note that changing the return water outlet from the top of the well to the bottom of the well will increase that static pressure, as I mentioned. So to overcome that bottom 200 feet of pipe is perforated. And that discharge pipe is perforated to allow that water return to migrate a little easier to the bottom of the well. Now, following these alterations, we then had a working system once again. This was 2014, and 8 years later, our well system is still fully functional, it's clean, it's efficient, and sustainable. We've integrated the system into our building automation system so we can monitor all points of the wells. Water levels, temperatures, pressures, etc. We have learned from our alterations and have lived through the growing pains as we modified our wells to work for our environment and our needs. So what have we learned? The wells provide a wonderful way to move energy to and from our buildings in conjunction with the heat pumps. They are quiet, not visible above ground, prevent heat island effect to some degree, and align with the sustainability goals of our university, our school, and the department, and provides an extended benefit of spreading a sustainable message among all stakeholders on our campus. They work well within the historical limitations we have in our yard. Our campus resides within an historical district, so an underground cooling system works well.
I should say people are always interested to hear about geothermal as well, visitors to our campus, so it's a great marketing tool. I will say, as I market it myself, that open loop geothermal wells are not a plug-and-play technology. How's that for an understatement? They take proactive work to keep them functioning and efficient. Connecting back to that description of that ever-changing column and fissures, we do redevelop our wells from time to time. We did this recently in the past few years. You see in this image here, trucks in our main Radcliffe yard drilling out the well. During this time, we get to see just how much iron bacteria can build up, even with the revised installation. There's a lot of water moving through a lot of minerals in these wells, so the iron bacteria is continuous even when we change the direction of the flow of the well. So this is where our BAS monitoring and preventive maintenance activities are really, really important. I can't even look at that slide because it just makes me so nauseous to see that much iron bacteria, sorry. We're always looking for significant pressure changes that might indicate that our filtration needs attention due to buildup, or that there's a buildup of iron bacteria or debris in the plate frames of the heat exchangers.
Yeah, a note about the heat exchange, the plate frame heat exchangers. Over time, they are the functional first defenders of the heat pumps. And throughout the course of their life, basically become a sacrificial clog point. So we can do some plate cleaning internally with our facilities teams, but eventually we need to send the plates off-site for refurbishing. We also see additional maintenance with the installation of bag filters we noted earlier. Those need to be periodically checked, cleaned, or replaced. And with our BAS system, we can see pressure drops on either side, so we know when they're faulty. There's an enormous amount of debris that you can see in this picture here that cleans out of the wells when it's redeveloped. You can see it's fairly substantial. And the same material can get circulated through the system and in effect create a liquefied sandpaper that can be catastrophic to equipment if not kept in check. With the wells operating at capacity, they offer cooling water to 11 heat pump units of varied capacities and can fluctuate their speed using variable speed drives depending on the load of the building. As a rule of thumb for us, we wanted about 90 gallons per minute of flow to each heat pump. And the wells offer us about 150 tons of cooling load when operating at capacity. So as you can see over this brief presentation, we have touched on so many of the IFMA competencies that are interwoven when dealing with facility-related equipment.
I guess to conclude, we'll offer some questions for discussion, starting with what are the benefits of geothermal wells?
What are the limitations of geothermal wells?
And thinking about what kind of operational considerations come along with maintaining geothermal wells, and beyond that, what variables you might consider when you're choosing between an open and a closed loop system.
I want to thank you all for your attention, and remember, please stay sustainable.